Alright, so with this one we're looking for how many litres of H2 there are in 26.7 grams of H2. So we'll start out with 26.7 grams of H2. And we know that grams of H2 will go on the bottom so that this can cancel. And we know that litres of H2 will be on top because that's what we want. And there's a relationship here between grams of H2, molecular weight in grams, is equal to 22.414 litres of a gas at STP. So we can just go ahead and say, well, that's 2.02 grams, that's the molecular weight, and that equals 22.414 litres. Now we can get away with this because they both equal 1 mole. If they both equal 1 mole, then they equal each other, and if they equal each other, then we can put one over the other like this, and we can say it was 22.414 litres of H2 for every 2.02 grams of H2, because they both equal 1 mole. The number of significant figures we get 3 significant figures because we started out with 3 significant figures over here, and that's how we'll end up with our answer. Okay, in the next one, we're dealing with 1 atom of mercury. We want to find out how much 1 atom of mercury weighs. I want you to realize that 1 atom is a very small thing, so we're expecting a pretty small mass out of this. So let's see how we would go about doing this. We start out with 1 atom of Hg. And we will have atoms of Hg down here as well. And we'll put atoms of Hg because we know that needs to cancel. Now what I've set up here is that 1 mole is equal to 6.022 times 10 to the 23 particles, where a particle can be an atom or a molecule. Now the atoms are when we're dealing with an element, and an element here is like mercury, and a molecule is when we're dealing with a compound. Now this isn't a compound, it's an element, so we're just going to stick with the atoms. And what we need here is a mass, so I'm just going to go ahead and put the grams of Hg on top. Now the relationship between grams of mercury and atoms of mercury is that we're going to have 200.59 grams of mercury, see that's the molecular weight in grams, and that's going to equal this number of atoms. Now remember, both of these equal 1 mole, so that's again how we can get away with this. We do 200.59 grams equals 1 mole, and this also equals 1 mole. So they equal each other, which means they can be put over each other like this. And that's going to give us our mass. That's going to be 3.31 times 10 to the negative 22 grams. Now I recommend here that in your calculator you enter the 6.022 times 10 to the 23 as 6.022 and then EE or EXP, depending on what your calculator is, 23. And if you do that, then this will keep it all together and you won't have to worry about order of operation problems, and you will end up with the mass that you want. And you can see it's 3.331 times 10 to the negative 22. That's pretty small. That's what we expect for an atom. Now just a word about significant figures. Now this 1 atom here does not count for significant figures because it's a counting number. Now you can't have 1.5 atoms or 1.3 atoms or anything else. You can have exactly 1 atom. That means we don't worry about that for significant figures. So what we're going to use for significant figures is the Avogadro's number, because that has 4 significant figures. This one has 5 significant figures. So our answer is going to come out to be 4 significant figures, which is what we get here. And again, just look at the magnitude of a number, how small it is, and that's what we'd expect to see for 1 atom.